Hello, and welcome to this lesson where we're going to learn how to design a passive filter. A passive filter is a filter with just basic passive circuit elements, resistors, inductors, and capacitors. And as hopefully you'll see, it's actually quite simple. There's only a few simple topologies to remember and a few simple equations to remember. We'll sort of skip over the heavy derivations, get straight to the good stuff so that you can get on your way designing passive filters. So let's just go ahead and get into it. Now, there are fundamentally four types of filters. Four types of filter. And they cover pretty much everything, right? So there's first what we call low pass. Then we have high pass. Then we have band pass. And then we have band, I read that as two twice, that's three, and then four. Then we have band reject. And the concepts here are pretty simple. First, if we look at just the low pass, what we're interested in doing is essentially creating a specific transfer function that fits a certain profile. So if we graph it out, what we want to do is have, on the vertical axis, we'll have the magnitude, the real component of our transfer function. Remember that S is equal to J omega, so we'll go ahead and write it that way. H of J omega, and on the horizontal axis, we'll just have frequency. And what'll happen is, at some point here that we'll call omega C, this is called the cutoff frequency. That graph will transition from 1 all the way to 0. This is for an ideal case. Obviously, in real life, it won't do this. But the idea is that for a low-pass filter, the transfer function will be 1, so it'll just let everything pass through undisturbed until you hit the cutoff frequency, and then it'll cut out everything. This section here, where we're allowing everything to pass through, is called the pass band, and where we're stopping everything is called the stop band. Now, for a high-pass filter, it's exactly the opposite. So let's say high-pass filter will have our vertical axis and our horizontal axis. That's still the magnitude of H of J omega. This is still omega. Now we have for a high pass, we only want the higher frequency. So at our cutoff frequency, then we'll go from 0 to 1. So whereas a low pass only allows things below the cutoff frequency, a high pass only allows things above the cutoff frequency. Then we have what's called a band pass, which is going to be sort of a mix of the two. Now what that's going to look like is this, and it's got a few extra parameters. Still the same setup though. The magnitude of the transfer function on the vertical axes. The horizontal axis is still frequency. And except now what we're going to have is we only want to let through a specific frequency. So we'll have our center WC is now not our cutoff frequency, but rather called our center frequency. And we'll have a WC low, a cutoff frequency low, and up here we'll have a WC comma H, the cutoff frequency high. And what happens is in this range, in this band, there is where we let everything move through undisturbed. So the passband now becomes this sort of floating region centered around the center frequency. So it's 1 in that region, and it's 0 everywhere else. Now we do have a new parameter here. The width of this region is called the bandwidth, and we're going to denote it with just a lowercase beta. And then there's also a thing called the quality factor, which we'll denote as Q. And Q is simply the ratio of that center frequency. Let me change that to make it not over the bandwidth. So basically, a passband filter should have as narrow a bandwidth as possible. See, as the bandwidth gets smaller, or excuse me, gets larger, the quality factor goes down, and as bandwidth gets smaller, the quality factor goes up. And that needs to be a ratio of what our frequency is. So there we go. Those are our 2 factors for bandpass filters. And finally, we have band reject, which is just the opposite of the band pass. And what that will look like is this. Still, the vertical axis is our transfer function, and our horizontal axis is our frequency. We have a center frequency, omega naught. We still have a cutoff frequency, low, and a cutoff frequency, high. Except this time, we're going to accept everything outside of this range. So we want to eliminate a specific frequency and let everything else pass through. And it still has the same things. We still have the width of this channel is still our bandwidth. And we still have our quality factor Q, which is equal to the center frequency divided by the bandwidth. So that's the sort of basic overview of all of our 4 fundamental filter types: band reject, band pass, high pass, and low pass. Now let's go ahead and take a look at how to design low pass filters using passive circuit elements. There are 2 circuits that we can use to design a low pass filter. The first is just called a series RL circuit, which we'll talk about in a second. The other one is the series RC circuit. Now the gist here, let's look at the series RL first, is going to be that we just have an inductor with some value L connected in series with a resistor. Let's go ahead and draw an extra terminal out here. So there's some value L for the inductor and some value R for the resistor. And on the left-hand side here, we have the voltage coming in, VI, and on the right-hand side, we have the voltage going out, V out. Now, to solve this, let's go ahead and solve the series RL. This will be the only one I do this particular one for, just because it's easy to see. We want to find our transfer function. So just remember that using the Laplace transform methods that we talked about in the previous lessons, remember that the impedance of R is just equal to R, and the impedance of L is equal to SL. And if we do a voltage divider for V naught, or V out, excuse me, it's going to be V out is equal to V in times R over SL plus R. And if we turn that into a transfer function, V out over VI is equal to R over SL plus R. Now to make it kind of a nice clean Laplace rational function, we're going to go ahead and factor the L out of this SL expression. So we'll have that our transfer function, let's just call it now H of S, is equal to R over L over S plus R over L. And in fact, we've now found the sort of general form of our transfer functions for low-pass filters. And that's going to be this, that our transfer function, h of s, make a little note here for low pass, is just equal to the cutoff frequency that we're looking for over S plus the cutoff frequency. Now this means that for our series RL circuit, if we come back up here, we can say that our cutoff frequency, omega c, is equal to R over L. Now for our series RC, we're going to have the exact same setup. Well, not the exact same, obviously, but we're going to have now the resistor on the top side and a capacitor on the second end, right? And we're going to take our voltage off of the capacitor. So just like before, we have plus Vin minus, and on the outside we have plus and minus V out, and we have R and C. Now, I'll skip over the derivation, but the gist here is that our our cutoff frequency, omega c, is equal to 1 over RC. So that transfer function, h of s, just looks like this, 1 over RC over s plus 1 over RC. Now, as you may have guessed, we're not going to get that sort of ideal curve for our transfer functions like we sort of expected. So if we go over to Wolfram Alpha, let's go ahead and do a really simple one. We'll just say that our cutoff frequency is equal to 10. So we found some values for R and L that would give us a value of 10. And let's go ahead and see what that would look like. So I'm going to flip over to Wolfram Alpha, and I'm going to go ahead and say I want to plot this. I'm going to plot the magnitude of my function here. And that's going to be, what, 10 divided by I, since we're using Wolfram Alpha, I times W for S plus 10. And I want to plot it over W. And let's go from 0 to, let's say, 30. There we go. So now we've got our plot here. Now notice that it's not that perfect sort of square curve. Instead, we have this thing starting at 1 and then falling off down, sort of infinitely down. We sort of determine the cutoff frequency. The cutoff frequency is where, let me write it this way. We're going to define it as this. It's the place where the magnitude of the transfer function for the cutoff frequency, so j omega c, is equal to 1 over square root of 2 of the maximum value, which for us is 1 of the transfer function. So it's where that plot is equal to 1 over square root of 2, which is approximately equal to 0.7. Now, if we go back and look at our graph, and we set it up so that our cutoff frequency would be 10 radians per second. Now, if we look at the place where on our curve, omega is equal to 10, and look at it on the vertical axis, you can see there that, yeah, it's about 0.7. So that means that our 1 over square root of 2, our cutoff frequency, is at 10 radians per second. So this filter is working the way that we hoped it would. So there we go. I think that is it for our low-pass filters. So we have series RL, series RC. For series RL, the cutoff is omega c is equal to R over L. And for the series RC, omega c is equal to 1 over RC. And then our transfer function is here for the low-pass filter is omega c over S plus omega c. And remember, our cutoff frequency in the non-ideal case is that it's the place where the transfer function, the value of the magnitude of the transfer function drops below 0.7 or 1 over the square root of 2. So that's it for low-pass filters. Let's go ahead and take a look at high-pass filters. Now, if you've got a good grasp on low pass filters, high pass filters are super easy because all they do is flip them over. So everywhere, essentially everything has been reversed, right? So for example, for low pass, we had a transfer function h of s was equal to the cutoff frequency over s plus the cutoff frequency. But for high pass, we're going to flip it over. H of s is equal to now s plus omega c plus s. See, everything is flipped over. And it's the same thing for the circuits. We also have series RL and RC high pass filters. But remember, if we flip over real fast to our notes on passive low pass, notice in the series RL we had the inductor and then the resistor, and we were taking the voltage off the resistor. And for RC we had resistor and capacitor, and we were taking the voltage off the capacitor. For the high pass filters, we're going to do exactly the opposite. The series RL will be the resistor and then the inductor. And we will take our V out off of the inductor. So we have plus minus V in, plus and minus V out, and we have R and L. One thing that's cool though is that the cutoff frequency equations don't change. The cutoff frequency for the series RL high pass filter is still just R over L. And for the series RC, we again sort of flip the location. We have the capacitor up top, and then we're going to pull our V out off of the resistor. So let's see, plus minus V in, plus minus V out. We've got C and R, and just like before, omega C is equal to 1 over RC. So let's go ahead and flip over to Wolfram Alpha, and we'll see how we just kind of change the equation and things work out just fine. So let's go ahead and plot, just like we did before. Hopefully I won't make that same mistake. So we're going to plot, and this time it's I times omega divided by, both parentheses, I times omega plus 10. We still want that cutoff frequency of 10. We're going to do it for omega, and we're going to go from 0 to 30, just like we did last time. Let's take a look. And there we go. Remember, we're looking for a cutoff frequency where the transfer function is 1 over square root of 2, or approximately 0.7. Now here you can see where it starts down at 0, or drops down as low as it can, and then rises up. So we're passing the higher frequencies this time. And just like before, our cutoff frequency was at 10. And if we look at where we are on the vertical axes for the transfer function at 10 radians per second, we're back there at 0.7. So this transfer function generates a high pass filter with a cutoff frequency at 10 radians per second. And that's honestly all there is to it for high pass filters. It's just low pass filters but flipped over. And we're taking off the other element. But the cutoff frequencies remain the same, R over L for the series RL, and 1 over RC for the series RC. So let's go ahead and move on now to bandpass filters, which are a little bit more interesting, but actually not that much more complicated. All right, so to take a look at bandpass filters, we're going to start with the series RLC bandpass circuit. There's a parallel, and we'll talk about that at the end, but we're going to focus primarily on the series RLC circuit. Series RLC circuit, and similar to all the other ones we've looked at, the way this one works is we have the input terminal connected to an inductor, connected in series to a capacitor, connected in series to our resistor, and we're going to take our output voltage off of the resistor. So let's see, we've got plus minus V in, plus minus V out, an L, a C, and an R. So first things first, let's go ahead and try to derive our transfer function. Just to quickly recap, don't forget our impedances for these things are our R impedance after we take the Laplace transform. Z sub R is equal to R, Z sub L is equal to S times L, and Z sub C is equal to 1 over SC. Now, just like we've done before, we're going to go ahead and solve for, or set up our voltage divider equation for V naught, which will be equal to VI times R over the sum of these impedances. So we'll have SL plus 1 over SC plus R. That's our V out. To make it a transfer function, we just divide out the VI. So we'll say that H of S is equal to V out over VI, which is equal to just R over SL plus 1 over SC plus R. So we need to do a couple of things to get this into that proper quadratic form for our transfer function. First thing I'm going to do is I'm going to factor out the L out of the first part of this expression. So that'll give us, up top we'll have R over L over, that'll leave us just S plus 1 over SCL plus R over L. The next thing I need to do is factor out the S from the 1 over SCL, and that's going to leave us with our final form here. So we'll have S times R over L on top over S squared plus S times R over L plus just 1 over CL. And there you go. That is our, let me change the color there. That is our transfer function for our bandpass filter. And there are a few parameters that we need to sort of outline when we want to go ahead and design it. For our bandpass, remember, it's all about those cutoff frequencies. So for the bandpass, we've got our cutoff frequencies. The one on the bottom, which we'll call omega CL, is just equal to minus R over 2L. And omega C high is just equal to positive R over 2L. For the center frequency, you might be just tempted to take the sort of average of the two cutoff frequencies, but it's actually going to be slightly different than that. We're going to use what's called the geometric mean of our cutoff frequencies for our center frequency. So the center frequency, omega naught, is equal to the square root of our two cutoffs. So CL times omega CH. And if you want to calculate that directly, it's just equal to the square root of 1 over L times C. So there's our center frequency. Now remember, before we talked about bandwidth and quality factor, bandwidth being just the width of the pass band. So bandwidth. And that's going to be denoted with beta, and that's equal to, here it's just the difference, so omega C high minus omega C low, or if you want to calculate it directly, you can do it with just R over L. And then finally, that quality factor Q is just equal to omega naught, the center frequency, over beta. But if you want to calculate it directly, it's the square root of L over R squared C. And that's it for the three main, I forgot to write that down, quality factor Q, our main parameters for designing our bandpass filter. So we've got our transfer function, we've got how to calculate our cutoff frequencies, our center frequency, our bandwidth, and our quality factor. So let's go ahead and work out an example of designing a bandpass filter using a series RLC circuit. Example. And what we want to do is design a series bandpass filter for, we're going to go from 1 kilohertz to 10 kilohertz. Those are going to be our cutoff frequencies. And we'll see what values we get from that. Okay, so the first thing we need to do is reconcile the fact that all of our equations are given in radians per second, but our design prompt was given to us in hertz. So first off, this 1 kilohertz is what we're going to call the cutoff frequency on the low side, and this 10 kilohertz is the cutoff frequency on the high side. And the first thing we need to do is just convert those guys into radians per second. So we can say omega C low is equal to 2 pi times the frequency C low, so that's going to be 2 pi times 1 kilohertz, so times 1,000 is going to get us 6,283 radians per second. And on the high side, we'll have omega C high is equal to 2 pi times FC high is equal to 2 pi times 10,000. And we're going to say that that's equal to 62,832 radians per second. So there's our sort of first step. The next thing we can calculate directly is our center frequency. Remember that omega naught is just equal to the geometric mean, so the square root of omega CL times omega CH. So that's going to be equal to the square root of 6,283 times 62,832. And that's going to be equal to 19,869 radians per second. So that's going to be our center frequency in radians per second. Now we're actually ready to go ahead and design our circuit. Now the best thing to do is you've got to pick one, and that sort of sets the tempo for the other. So what we're going to do is we're going to choose totally arbitrarily. Now when you get a little bit more advanced and you start applying this in your actual engineering work, there will be reasons to choose some capacitor values over others. Some capacitors work better for sort of audio frequencies, or versus RF or microwave frequencies. So, but for now, we're not going to really care. We're just going to sort of arbitrarily choose. We're going to go with C is just equal to 1 microfarad. And then from there, everything else sort of spans out. Now, the equation that we can use, let's find L first. If we look at our original equation for center frequency, omega naught is equal to the square root of 1 over LC. So we can do a little bit of algebra and a little bit of rearranging to get that equation so that we can solve it for L. So that would be, let's first take the square of both sides. Omega naught squared is equal to 1 over LC. And that means that L is just equal to 1 over omega naught squared times C. Let's put some real numbers behind that. I'll say that L is equal to 1 over omega naught, which was 19,869 squared, times C, which we chose to just be 1 times 10 to the negative 6. And that's going to get us an L of, punch that in your calculator, 2.5 millihenries. There's our inductor. So now the next best equation for our resistor is going to be just bandwidth. Bandwidth is equal to R over L. So we can rearrange that and just say that R is equal to bandwidth times L. Remember, bandwidth is equal to, actually, you know what? Instead of chalking it up, because we'd like to know what our bandwidth is, so let's actually go, well, so R is equal to bandwidth times L. Let's calculate our bandwidth real quick. We know that bandwidth is just equal to omega c high minus omega c low. So that's going to be equal to, what, 62,386? No, 382, 832 minus 6,283, meaning that bandwidth is equal to, where's my calculator? There it is. 62832 minus 6283. Our bandwidth is equal to 56,549. 549 radians per second. So we can now punch that into our equation for R. R is equal to what we just got, 56,549 times 2.5 milli, so 2.5 times 10 to the negative 3. And that's going to get us a resistance of 141 ohms. And there we go. There's all of our components. R is 141, L is 2.5 milli, and we chose C to be 1 microfarad. So let's go ahead and draw our circuit here, just for fun, just to say we did. Let's see, we've got our inductor at 2.5 millihenries. Connected that capacitor at 1 microfarad. Connected to our resistor at 141 ohms. And our input and output terminal. So there is our designed bandpass filter. VI minus plus V out minus. Now there's two more things that I'd like to do before we call it quits on this particular example. The first one is let's go ahead and calculate that quality factor just so we can see what that is. Remember that Q is equal to center frequency over bandwidth, which for us is going to be, let me go find those values, 19,000 869 over our bandwidth, which we found to be, what was it, 56549. And that's going to give us a quality factor, a Q of 19,869 divided by 56549 of 0.351. 0.35. Now this is actually a really bad Q. Typically you want, high Q filters have Qs in like the integers, 5, 6, 7, 8. So a Q that is a fraction is actually really bad. Passive filters are generally considered not very high quality filters. So that's why we have Q values here that are so low, or that's indicated by the fact that we've got Q filters here, or Q quality factor here that's so low. So this is a bad quality factor. But that's okay. It doesn't mean our design is bad. It just means that passive filters don't have great quality. So the last thing we're going to do is I want to go ahead and try to plot this. So let's go ahead and bring back our transfer function. And remember that that was equal to S times R over L over S squared plus S times R over L plus 1 over 1 over LC. Now remember, 1 over R over L is just our bandwidth, so we could rewrite this real fast as S times beta over S squared plus S beta. Now something up here is our 1 over LC. What was that? Square root. Look at that. The cutoff frequency, omega naught, is the square root of 1 over LC, which means that 1 over LC is just going to be the center frequency squared. So there we go. There's a much more concise way of writing our transfer function. Let's go ahead and put the values that we calculated for all of that in. So h of s is equal to s times, what do we get for beta? 56,549. So s times 56,549 over s squared. S times 56,549 plus the center frequency squared. So what is 19,869 squared is a big old number, 394 times 10 to the 6. And it's 0.7 times 10 to the 6. I'm going to write it as 395 times 10 to the 6. I like to play it fast and loose with my rounding sometimes. So let's see. Let's go ahead and flip over to Wolfram Alpha and see if we can plot this guy. So here we go. I'm going to plot. I'm interested in the absolute values of, or we got S's, so that's going to be I times omega times 56,549 divided by first off that s squared, so I times omega squared plus I times omega times 56,549 plus 395 times 10 to the 6. Let's make sure I close that parentheses. And I want to solve it for omega. And let's see, our cutoff frequencies were sort of big, right? We had, what do we have? 6,000. So let's go ahead and start at, let's start at 0, and let's go out to 100,000 radians per second. Let's go and see what that gives us. That does the thing. Okay. So let's take a look at this curve. Our center frequency, our place where it should be 1, was 19,869 radians. So let's just go ahead and clock in at 2,000 or 20,000 radians. And yeah, that sort of checks out at about 19,000 radians per second. We seem to get that peak there at our transfer function equal to 1. And then on the low side, let's see, we're looking for 0.7. So that's like right there. I don't know, that's probably about 6. Yeah, so if that's going to be 10,000, that's going to be 5,000. That means that right there is probably going to be about 7,000 or 6,283 radians per second. And then over on the flip side, remember we had 62,000. So that's going to be right there. So yeah, so on the high side, 62,832. That looks pretty good. So yeah, so you can see that it's not that ideal sort of rectangular curve. It sort of, in fact, does this kind of weird sort of high peak and then tapers off. But what you're looking for is, and this is kind of why we said that, passive filters aren't that clean or don't have that much quality factor to them, because they still let an awful lot of bandwidth get in there. So the bandwidth on this guy is pretty huge. But that's a good looking filter, and that seems to work out just fine. Let's go ahead and the last thing I want to talk about before we move on to band reject, our last topic here, is that you can make a parallel RLC bandpass with very similar parameters. So I'm going to call this the parallel RLC bandpass. And the way this guy is built is we have the resistor first at value R, and then we have the L and the C in parallel. So we have the inductor, with value L, and the capacitor with value C. And we take our output voltage off of the L and the C in parallel. So input here, plus minus VI, and output plus minus V out. And the equations for our main parameters are just slightly tweaked a little bit. We've got that our cutoff frequency low is equal to minus 1 over 2RC. Our cutoff frequency high is equal to positive 1 over 2RC. Our bandwidth is just equal to 1 over RC. And our quality factor Q is going to be equal to the square root of R squared C over L. And that square root is sort of covering the L as well. And that's all there is to it. We won't worry about working an example of this because it would be the exact same process that we saw for the series. I just wanted you guys to be aware, and I think you've got some homework problems that ask you to design this parallel RC bandpass filter. So that is it for bandpass filters. Again, hopefully you saw not super complicated, but a little bit more interesting. We've got some interesting curves that come out of them when we look at our transfer function plots. Last up, let's talk about band reject filters. Band reject filters are pretty easy. It's the same parameters as the band pass filters as far as the cutoff frequencies and the bandwidth and the quality factor and the center frequency. Everything is exactly the same. There's just a slightly different transfer function, which we'll write down now. And then we'll go over the topologies for this series and the parallel RLC band reject filters. The transfer function, h of s, is given as s squared plus 1 over LC, or actually we're going to write it here as the center frequency squared over s squared plus the bandwidth, beta, times s, plus the center frequency squared again. And then for the series RLC band reject, remember that transfer function governs both of them. So the series RLC band reject, it looks like this. We've got our input terminal, and then it's kind of flipped over from the series RLC bandpass. Here we've got the resistor R as the first element, and then that's broken out in series with the inductor and the capacitor. And so we'll take that output voltage plus minus from the node that's covering the inductor and the capacitor, plus minus V out. Oh, and I should have labeled L and C. And then we have our input side plus minus V in. And then our two core parameters here are the center frequency, omega naught, is equal to the square root of 1 over LC. And the bandwidth is equal to R over L. That's the series band reject topology. Once you have that, everything else is the same as for the bandpass, and you can design your filter to fit those parameters. Second up, or last up, is the parallel RLC band reject. LC. Which has kind of an interesting topology. It looks like this. We have our input terminal, and then we break out, remember, because we have to like flip things over, we actually break out the inductor and the capacitor in parallel up here at the top. And then we tie them in, and that feeds to our resistor node down there. And then the output node, that's kind of a messy drawing. But we've got L, we've got C, we've got R, and then we have plus minus V in and plus minus V out. And the parameters for the parallel band reject are the same as they were for the parallel band pass. We'll have a cutoff frequency at, again, the square root of 1 over LC, and a bandwidth equal to 1 over RC. So with those parameters, you've got everything you need to design our parallel RLC band reject filter. And that's it for band rejects. It's got the same structure, like I said, the same design process, the same calculations as the band pass filter, just a slightly different topology. And that's all there is to it, and a slightly different transfer function. So there we go, band reject filters. So there we go. That is it for our passive filter circuits, right? We talked about low pass, we talked about high pass, band pass, and then finally band reject. And actually that is everything for chapter 14. In chapter 15, we're going to talk about active filters. So these are filters, still low pass, high pass, and band reject, but these are going to use op amps to sort of beef things up a little bit. Remember, our passive filters had very low Q values, very low quality factors. By using active components, specifically op amps in this case, we can actually raise the quality factors to get good quality factors of 6, 7, 8, what they call high Q filters. So that's what we're going to talk about in the next lesson. I know we went through a ton. This was a long video, about 50 minutes all in all. But thank you for sticking it out with me. So as always, if you have any questions, comments, concerns, please let me know. And if not, I'll see you guys in chapter 15, where we're going to talk about active filter circuits.